Right. And hopefully people do know that hopefully the YouTube things will be good. I do see that people actually are watching the things on YouTube, which I totally appreciate. And I think that's good. And I hope that means the link is working and stuff. So yeah, and that's again, of course, the only reason we're recording them. Great. Okay. So we're here. Just to be clear, I think this whole method I see that people are submitting for the points, which is great. It's making me happy. And hopefully, you know, more and more we're doing this more and more of your points can come from this and less even concerns about homework or something like that, because everybody's lives are so complicated. So it's really, at least for me, making a difference in class. Like I can feel the difference. And so you haven't got more and more, I'm owing you guys points. Every time you submitted one of those things, yes, the points are going in and I'm seeing them and you will get them. I don't want to do more of that. So I want to make it, hopefully you saw today. Again, we're going to do this thing where if you say anything at all, submit it for the points. If you say something that's subject to, if I say it's right or it's wrong, you could submit, you can double dip and submit that also for points. I want to make it clear that if you weren't here last week, or if you don't know what I'm talking about, especially, or if you weren't here last week or you missed a class or something, I just updated those assignment portals to still be due. Like there's no lateness on this. This is like, if you say something in class, submit it. And so it can be retro. Like if you weren't here last week and you want to say 4 things today, you know, you could submit 1 to each. Whatever is the generous interpretation of this, assume that that is the interpretation. And I don't want it to get too complicated, but believe me, if this keeps going, I'll add more point structures in different ways for different ways to get more points, whatever. So that all said, we're going to keep going. Oh, sorry. Oh, sorry. So is that, let me see. Right. Like, yeah, like update just in the sense that I'm saying, basically you should all assume, I mean, Heaven and everybody, like even what she just said, like that would count, right? She just said something. She just asked a question about the class and was willing to go public with it. So right away, she can write that down on a piece of paper today and submit it to the assignment portal that said like, that said today, like a game, take 3, because it's like the 3rd assignment portal that I put in for that. She could put it in for there and get the points. But say she says another thing later on today in class, but if this is what I mean by update, or what she means by update, she can, if for whatever reason she didn't say anything last week, although I think she did, or she wasn't here last week or something, she could take one of those assignments when I wrote a game, take 1, like when I wrote it last time for the last class, she could take that one and put another comment in from today into there. Like, I don't care what day it was that anybody says anything. It all counts is what I'm, so yeah, update like that for sure. And I'll just try to, so every time you see any of you, if you ever see an assignment portal in your stream that says the word game in it at all, you should also know that's not new, more homework to stress you out. That's just another portal for you to like submit a comment for points. That's all it all is that. I mean, you know, submit record of a comment you made in class for points. So if you ever see the word game, don't think it's like new, crazy, stressful homework or something like that. It's all of that. Hopefully that makes sense. But now what we're going to do, because I think this is working, actually, we're going to move on in the material here. We're going to move on in the material here, and very formally now start what we really did start with lab 3 and lab 4, and what we sort of started talking about in the question I raised last time. We're now officially moving to the next chapter, if you like, called 2-dimensional kinematics. I'm going to write that for you in a second, but I want you to see what's on this first page first. We're moving to the topic of 2-dimensional motion. We have been doing 1-dimensional motion. The whole theory is that we understand all of what there is to understand about motion within a line. So if we now move to the plane, so to speak, if we open up our horizons and acknowledge that like space involves more than just a line, the whole method that we're going to try to nail down is a method that will just allow us to treat the plane as 2 separate, independent, but simultaneous lines. Like we're going to figure that everything we understand in this axis also applies to this axis, and anything that's going on at the same time in both axes, we're always just going to separate. Oh, here's what's going on here. Here's what's going on here. Oh, they're happening at the same time. Like that's how we're going to think of it. So we're going to, and that's going to work for any number of dimensions. Once we get, in other words, how to move from 1 dimension to 2 dimensions, that process, that technique called vectors, is how we're going to move from now on to any number of dimensions that we ever need in a physics problem. 3 dimensions, 4 dimensions, 11 dimensions, like some people believe in, whatever it is. So the new topic here, just to make it clear, sorry. Oh, sorry. The new topic here. Well, maybe I said this. Sorry. Sorry, the new topic here. Okay, just to be as clear as I can be, like the topic that we're moving to now, technically, formally, is called the vectors. It's called motion in 2 dimensions, 2-dimensional kinematics. The way we navigate, the new tool we have to learn in physics for navigating 2 or higher dimensions is called vectors. Now, in some ways, we've had vectors all along already in our lives. A vector quantity, just to remind you, is a quantity with size and direction, right? Like speed is not a vector quantity. Speed is like you're going 30 miles an hour, but velocity is a vector quantity because you're going 30 miles an hour positive or you're going 30 miles an hour negative. It makes a difference. We're continuing with that idea of dealing with quantities that have both size and direction, but now we're expanding our horizons into more than 1 dimension at a time. So direction gets more detailed and more complicated now. The thing that we're going to use to represent vector quantities are called vectors. Vectors are arrows that represent quantities with size and direction. Let me just say that one more time. Vectors are arrows. You might want to write this down. Vectors are arrows that represent, actually, I'll even write it, sorry. And then we'll get to the question. There's a question I want to ask everybody, but all right, let me make this as clear as I can. Okay, just to be super clear, oops, sorry, people. We're dealing with motion in a plane, motion in more than one axis at a time. That's what started happening in lab 3, even though it was just drawing. And then lab 4 in particular, you had a gun, right? You had something that was fired forward, but also fell down. So we had to deal with 2 dimensions at once. The way we deal with dimensions the way we deal with vector quantities in 2 dimensions or higher is we use arrows to represent vector quantities. Like instead of just writing numbers on a piece of paper, we draw arrows on a piece of paper, and every arrow represents a vector quantity very conveniently because an arrow has size and direction, just like a vector quantity does. And we use them deliberately that way. That is, we try to draw things to, once we draw a drawing, we try to make it somewhat to scale, so that if we want to represent a velocity of 20 miles an hour, we might draw a certain arrow. But if we then wanted to represent another different velocity of 40 miles an hour, we would draw a longer arrow, an arrow twice as long, and would have its tip point in whatever direction the velocity points. Okay, so we're going to use arrows to represent vector quantities. And anything we're going to do here today with displacement vectors will apply to any kind of vector quantities, whether it's displacement or velocity or acceleration or force or field or everything in physics. Okay, having said all, so that's what we're doing now. That's the land we're in formally now, motion in higher dimensions. It's no new formulas, it's no new equations, it's just a new technique for putting together the equations that we have from one dimension, relating them to any other dimension. So here's the question I'm going to ask everybody, like that you're all going to do for points now and blah, blah, blah. The question I'm throwing out to you, that it was not a homework question or anything like that, like we're looking at it fresh right here, but you've seen versions of it in lab 3 and in a way in lab 4. So I'm going to ask you to figure it out any way you want, through drawing or through computation or through both. So the question is this. Sorry. So, well, the givens of the question are here, like on the first page. You might have already written them down, but so the givens are, imagine, the givens are, imagine that I walk, or you walk, whatever, a person walks 5 meters due north. So a person walks 5 meters due north, and then like has a glass of water, whatever, pauses, and then walks 8 meters, but now northeast, somewhat north, somewhat east. In fact, specifically 30 degrees northeast. Okay, I'm going to draw that for you in a second. I want to make this but that's the situation. I haven't asked the question yet. The situation is that the person walks 5 meters due north and then picks up where they left off and walks 8 meters at a northeasternly angle of like 30 degrees. You could probably imagine actually what I'm going to ask. What I'm going to ask is, how far did this person get in total, and precisely in what direction did they end up getting? In other words, what I'm going to ask is, what's the total displacement, the resulting displacement from having added these 2 displacements together? In effect, this is like lab 3 again. That's what I'm going to ask. And if you're already on, you can start working on it right now. If you're like bored of what I'm, if you think you got it, you can start drawing, you can start figuring it out. But let me say to all of you, that is what I'm going to ask. But I will tell you, of course, I did this in the last period. This question is like a good physics question. It's super simple to state. And I like to think it's super fair and obvious. Like if I say I walk this way and then I walk that way, I think it's very fair and obvious that someone might ask, how far did you go and where did you go? I think it's fair and simple to ask, but I do not think that the answer is easy to get. Like I cannot do this in my head. Like the answer is not 13, for example. The answer is not 13. It's something smaller than 13. It's something bigger than 8, and it's something bigger than 5, but it's not 13. I cannot do it in my head. I know it, I did it, but it does take even me like a minute. I don't mean even me, but so you have to think this through. And I'm going to give you some hints right now to like, in terms of how I'm imagining the world. Oh yeah, I think I just lost. Did I just lose you all? Wait, did I just lose you all? Oh, no, you're still there. Okay.
No, we're here.
You're there. Okay, thank you. All right, I don't know. So I want to, so you could start working on it if you want, but it might be hard to start working on unless I establish a couple of things about how we're going to picture the world here, like exactly how I'm using numbers and directions. Remember from physics, remember from one dimension, from Galileo and everything, that even if we're in one dimension, we always have to start by making a choice of coordinate system. We have to choose like which way is positive and which way is negative. And then we can choose whatever we want, but then we have to stay consistent with it. Same thing here, but there's a lot of choices to make here. So we might all want to stay consistent together, at least at first, i.e. I'm going to say, here's the world I'm living in. It's got north-south. It's also got east-west, just like lab 3. So I'm setting up a coordinate system where, sure, I'll put east-west like on my x-axis. I'll put north-south on my y-axis. And each axis has its own positive and negative designations. Each axis is its own independent 1D world. So I'm going to say that anything that goes to the east, like anything that goes to the right of this, is called positive. And anything goes to the left, in other words, west. So I'm looking at my blue drawing here. This is like a big mess. Hold on a second. I'm looking at the blue coordinate system. So east is positive, whereas west is negative. But also, at the same time, north is also positive while south is negative. Two independent worlds happening at the same time. So you can picture what due north means, just like up that y-axis arrow. Due east would be just go straight over. But what about these angles in between? Well, it is like math class, although we do it a little bit differently from math class, but it's like math in that we are always going to open up our angles from that positive x-axis or that positive east axis, if you like, or in other words, what people call due east. Like if you look at the arrow that's pointing due east, that's like my reference. That's where I'm going to start opening up any angle. But then I'm going to open up the angle like counterclockwise up in the first quadrant, just like math class. And that angle there, theta, that's what I mean when I say, well, that angle there, theta, is how we're going to precisely define directions from here on. Like I'm saying, from now on, and we're in the plane, we're in 2 dimensions. So from now on, if I ask someone how to get to the post office and they say walk 3 miles, that's not good enough, right? We're like 3 miles to the post office. Okay, but where, in which way do I go? So then if they go, oh, 3 miles positive, like even if I'm a physicist and they're a physicist, that doesn't make any sense. Like in my neighborhood, you can't say 3 miles positive. Like, what do you mean? Do you mean downtown, uptown, crosstown, east town, west town? But if they said, okay, go 30 degrees, if they give an angle, then that's precise. And that will tell me which way to go, as long as we all agree on how to measure these angles. So I'm saying, if someone says to me, go exactly north, I know what that means. That means like straight up that y-axis arrow. If they said, and same thing if they said go due east. Similarly, if someone literally says to me, go northeast, like exactly northeast, like due northeast, go that way, Yaverbaum. If they're really serious that they're using the words carefully, I would know if they say due northeast, I figure they mean as much north as east, like somewhat north, somewhat east, but even Steven. In other words, I'd figure they mean 45 degrees between the east line and north line. And that would be right. Like, and if that's what you guys are thinking, you are right. But I just want to make this clear because it gets a little bit tricky after that. So if someone says northeast, they mean 45 degrees northeast. In fact, if you really think about what they mean, and here's the new part, if they say northeast, what they're really saying, and you look at the bottom of the page here where I wrote in blue, northeast really means north of east, if you really think about the way we're opening up these angles. If they 45 degrees northeast really means start at that eastern line and open up an angle 45 degrees north of it, right? 45 degrees northeast really means 45 degrees north of east. I just want to make that clear to everybody, because now we can say something. Then if I say something like 30 degrees from now on, like I'm saying in this problem, I'm saying picture me first walking north for a while, but then picture me walking 30 degrees northeast. What that specifically means is 30 degrees north of east. It means that the angle, the direction I'm going in is actually less north than it is east, if you know what I'm saying. It's not 45. 30 degrees northeast means 30 degrees north of east, which is the same thing as if someone had said 60 degrees east north. Now that's an awkward way to talk. People don't talk that way. People say northeast or they'll say southwest, which tells us, like, since people always say northeast or southwest, but you never hear a normal person like in an airport or on a ship go like, oh yeah, you gotta go east north. No one says that because we don't open our angles. That means that we should always be measuring our angles from the horizontal. If we want to get numbers that make sense to normal people, or go back and forth, or be north, our angles here are going to be like northeast or southwest or southeast. But that, you'll see why. So I'm saying we measure angles from the horizontal. Just it's always measuring from east west. Measure. You'll see how that. Okay, but all that said, then that's just to ask you to picture, so that hopefully we're all picturing the same thing, that in the problem of today, we're picturing Right. We're picturing, and I'll put a picture, I'll actually put a picture in a second. We're picturing that I first walk 5 and then I walk 8, like at 30 degrees northeast. And I'm going to ask you all, I'm going to draw one more thing and then I'm going to shut up. I want to know that my total displacement, but I have to make it clear that means what I want to know. So this will take a minute or two. It'll take a lot of minutes. I, as a final, and you could say right or wrong things and get tons of points, but to know, to actually have a final answer to this question, what I'm going to need is a total distance, like how far did I get? And I'm going to need a direction. I'm going to need an angle for the final answer. And it won't be an obvious thing like 45 degrees or 0, like you actually will have to do math to get it. The final answer will be a final distance and a final direction, like blah, blah degrees northeast or blah, blah degrees southwest or something. That's what I'm going to be looking for. Last thing to say is how, yeah, well here, okay, so here is the situation. I walked 5 meters from like a certain start, then I walked 8 meters at that angle. If you look at the pink arrows that I drew, this like this thing right here, that's a small sketch of the whole situation. It is a sketch of the situation. And if you sketched it very nicely, like better than me, like you actually drew everything to scale or on a piece of graph paper or something, then like lab 3, what I am actually telling you is, yeah, what you're looking for is this dotted pink arrow, this third arrow. Like if you walk 5 and then you walk 8, notice my second arrow is like longer than my first, but not perfectly well, but I walk 5, then I walk 8 at some angle. What I want to know is how far did I walk in total from the original starting spot to the final landing spot. In other words, what I am saying is, if you want to, I'm asking you to add 2 displacement vectors together to get a final displacement. And I'm telling you in advance that actually you could get this by drawing. You really could. We trust the arrows that much that if you drew the 5 and then you drew the 8 accurately, like to scale and at the right angle, at the correct angle, then that final leg of that triangle, if you measured it and measured its angle with a protractor, it would be the right answer. Now that's one way you can get this, and you totally can. But that's hard for a lot of people. It's hard for me to draw that well, and it takes a long time. So there's other ways to get it without drawing it perfectly, but that is what I'm looking for, is the size and the orientation of that final angle. In other words, we're adding 2 vectors, and one method you could add vectors by is by drawing them tip to tail. But but you don't have to do that. But I'm looking for, in the end, right here, a length and an angle, a final answer. And the final answer will be, it will not be exact pretty numbers. They're not numbers you can come up with your head. One number is like a little bit less than 13, and the angle is a little bit more than, it's more than 45, but it's less than 90. So I'm just going to shut up. And I can't imagine anybody would just get in one. Well, it'll take, oh, let's see. Okay. Oh, wow. Okay. Sorry, so I'm responding to the chat, but yeah, go for it. Anybody, I'm looking in the chat here, but. Wow. Yes. Wait. So I'm saying yes to Ardell. Wow. Totally yes. Game over for Ardell. But that was fat. So do you want, that's, and I'm getting some things in the private chat too. So I'm a little bit, but that's totally awesome, Ardell. I don't know if you want to explain it or let it have, but that, yes, that is correct. That's awesome. Do you want to explain anything or say anything about what you did? But that's total points, obviously.
Okay, so first I did the diagram. I did 5 meters north and then 8 meters 30 degrees northeast.
Right.
So I drew like a triangle from the 8 meters, and I used trig to get like the other 2 sides. So I turned the 8 meters into 2 different vectors.
Yes.
And yeah, I got 4 meters north and 4 radical 3 as the horizontal thing. And then I added the north to the already given 5 meters because that's the total north displacement. And then I left the 4.3 by itself because that's just east. That's a different one. Right. And then I made a new triangle and I used the 9 meters as one side north and then drew another vector going east, that's 4 radical 3. And then I used Pythagorean theorem to get the third side, to get the displacement. And then I used inverse trig to get the angle.
Serious, wow. I mean, and I don't want to, again, I don't want to overreact or anything, but that was seriously awesome. I mean, and again, I want everybody to understand that even if every little thing she just said was wrong, point wise, it would still be like oodles of points for how gutsy and specific, but also every single thing she just said was right. And yeah, wow, thank you for the class support for her. Yeah, that was so right. And I got it. And two, I'm always afraid to like overcomment something because I always feel like it's like me walking in a room and someone saying like, wow, oh, you look so thin, you look great. And it's like, oh, well, what are you saying about what I looked yesterday? Or something, you know, I mean, I don't want this to be a comparison to what anybody ever did yesterday or something. But one thing that was so good about everything she just said, and it was fast, by the way, you know, that was a lot of steps she did. And there's no way you could make up, I know those numbers. I know them because they're sitting on my page. Those numbers, you can't fake those steps. You can't make up those numbers, and nobody can do all those steps just at once. So that's some serious work, but I got to say, and it's correct. It's exactly, I'm going to draw it for everybody my way, but that is my way. That is the way to add things. And I knew she knew exactly what she was saying or what I wanted to hear when she started like, it wasn't the very first thing she said, what Ardell said, but like one of the early things Ardell said was that she broke up the 8 triangle into 2 pieces. Once she said that, I knew, okay, yes, we are doing the right thing here. Anybody who gets that in order to add the 8 to the 5, you've got to break up the 8 first. That's a key insight. It might seem even obvious to her. I don't know at this point, but that's a major insight of doing this, doing this by what's called the component method. Again, I'm going to draw it for everybody no matter what. I'm not saying class over just because but I will say also, say this was an exam right now, say that was a problem, which, you know, could, and say that what she just talked out was more or less what was on the piece of paper. One of the reasons it's such full credit, and it's so, and I'll move on in a second too. I don't want to make too big of a deal, but one thing that was cool about, and she said a lot, right? Like that was a lot. There was a lot of room to be right or wrong in a lot of that, but it was all right. And the thing about it is, she said it just similarly enough to the way I'm about to, that I know it's right, but just differently enough from the way I'm about to, that I know she actually gets it. And that's what you all want to do on exams, is you want to do things like we do it as physicists enough to show us that you get the fit, but you got to do it your own way. She said some of those things in a different order from the way I would, or use some different language here. And then but like, you know, she covered every ground down to the inverse trig at the end, which I might use a different word. But the fact that she's doing it her way, it shows she's not spitting back something. It shows she obviously, it's in her. Okay, I'm going to stop complimenting, but yeah, that was right. So now, also, I think I'm complimenting because it takes the wind out of my sails. I got nothing interesting to say now, like punchline over. But yes, what she's doing is she's adding the 2 vectors by what's called a component method. It means that we're going to, from here on in, and this method works for as many vectors as we want. Like right now, we are adding 2 displacement vectors together, but this method that we're doing will work if we're adding 3 or 4 or 5 or 1 million displacement vectors, and it'll work if we're adding 1 million any kind of vectors, even if they're hard to picture. And the key to the method is one of the first things she said. This is what I do right away, and what Ardell was saying is, I'm going to the principle that a 2-dimensional problem is just 2 one-dimensional problems occurring independently yet simultaneously. So I'm going to break this world. Again, this is just my words for what you just did, but I'm going to break, and really, it's not, I always take the world, if I have a 2-dimensional situation, I'm going to break it into the X world and the Y world. And I'm going to say that what's happening in each world happens independently. And the way I'm going to do that is I'm going to make a chart. I always make an XY chart. And I really do, by the way. I literally do make this chart, even if I'm talking about fields or anything complicated. Like the more complicated it is, the more I have to make this chart for myself. It's not like a teaching technique. It's a thing. And the point of the chart is you have the X dimension in one column, the Y dimension in another. And then the row entries in this chart are going to be each vector that you're adding together. Like today, in this case, we just have 2, but we can have as many as we want. So I'm going to put vector 1 in the first row and vector 2 in the second. And what I'm going to do to each vector is exactly what Ardell did. I'm going to zoom in on each vector. And I'm going to look at each vector and say, what impact are you having on the x-axis? And separately, what impact are you having on the y-axis? Like, how far do you take us on each axis? What Adele said was she looked at the first vector. She zoomed in on, I don't remember which one. We zoom in on that first vector where it says up 5 meters, right? So here I am, number 1. And that first vector, like she said in English, and it just only requires English. Like, I don't have to do any math. I just look at that picture and I know what Ardell said, which is, yeah, that vector takes you 5 meters north, and it doesn't take you any amount east or west. In other words, if I'm entering that vector's progress into my chart, I'm going to say that vector took me 5 meters to the north. And north, remember, we're calling positive. So it took me like positive 5 meters. If it had taken me to the south, I'd make this a negative number. And it took me nowhere in the east or the west, right? And that's what and that's just from looking at it, from the picture. But then the second vector, okay, takes a little bit more. This is where she hooked me in. The second vector is 8 meters at 30 degrees northeast. Now notice that 30 degrees is north of east. Notice that 30 degrees has nothing to do. Now, this is me talking now. I mean, this is not me correcting Ardell either. It's in agreement with her. But this is a detail to emphasize here, that 8 meters is drawn from its own little 30 degrees. It literally is 8 meters north of an imaginary, objective, or personal x-axis that this 8 meters carries around with it, like its own personal savior x-axis. And if I think of it that way, that the 30 degrees is just its direction, just like technically the 5 meters has a direction of 90 degrees. I just don't really have to look at it. But here I look at this 8 meters and I do trig, I do SOHCAHTOA. I say, or she said, Ardell says, okay, sine of 30 degrees sine of an angle equals opposite over hypotenuse. Cosine of the angle equals adjacent over the hypotenuse. That's how you learn it in math. I switch it around in physics. Usually in physics right away, what I'm looking for is the sides. I usually have the angle, as is the case here. And so I'm saying those two sides are hypotenuse times the cosine and hypotenuse times the sine, adjacent and opposite respectively. And those are just numbers, right? And I can stay on this page if anybody wants me to, but I'm just blowing it up. On the next page, it's just a repeat of that, just zoomed in. On the next page, and here's what Ardell like literally said out loud. And this is the physical part, and I really need to emphasize of course, it's like everything in physics. Once you get it, then you get it. And it almost seems like you can't imagine not getting it maybe, but until you get it, you don't get it. So, and that's everybody at any time. So looking at this triangle, notice all this work I'm doing with right triangles, I haven't added anything yet. Like Ardell didn't add anything yet by just zooming in on the triangles. Put another way, I'm doing we're going to do like SOHCAHTOA and Pythagorean, like triangle stuff here. But the triangles that I'm analyzing, or the triangle that I'm analyzing, is just formed by the 8 by itself. It doesn't even have to do with the 5. Please note, and I'll repeat that again in a second. But all we're doing now is breaking up the 8 and saying, oh, I get it. It's like in Lab 3, or it's like in Manhattan. If you got to go 8 blocks to the northeast, you can't walk through buildings, or at least some buildings you can't. So you got to think about how far you're going uptown separately from how far you're going crosstown. And just from the trig, what this triangle shows is to go 8 at 30 degrees northeast is equivalent to going 4 north, while at the same time going 6.92 approximately east. Notice how carefully I'm drawing this. I'm literally saying that going 6.92 to the east horizontally, like I have an arrow here with a tail and a tip, and then I'm starting a new arrow at the tip of that. Ardell's going I start by going east 6.92 meters. Then from the tip, I go north 4 meters. So I've drawn 2 arrows tip to tail, and I'm saying their sum, the resulting displacement, is the final arrow that completes the triangle. In other words, before Ardell even adds the 8 to the 5, before she adds this 8 to anything, she actually asks, well, what 2 things could have been added together to make this 8? And in a 2-dimensional plane, you don't add 4 plus 4 to make 8 or something like that. You add 6.92 plus 4 to make 8. If you see what, because direction matters. Like to go 6.92 purely east and then go 4 purely north is, according to this triangle, equivalent to going 8 at that particular angle of 30 degrees northeast. So she got the equivalence. This is called resolving. What this triangle here is resolving the vector, in this case the 8 vector, into its components, into x and y components. All it did was resolve the 8 into 2 smaller pieces, but those smaller pieces are the ones that she did and I can put back into the chart right here. In other words, she said the second vector took us 6.92 to the east, as well as at the same time, but independently taking us up 4 to the north. Like, and you know, again, that could have happened to have been south, in which case it would be a negative sign, but everything here happens to be positive signs. So then now we have 2 independent addition problems. Like once upon a time, we walked 0 to the east, and then we walked 6.92 to the east. So we walked a total of 6.92 to the east, meters to the east. And once upon a time, we walked 5 to the north, and then we walked 4 to the north, right? So we walked a total of 9 to the north. That's what she's saying, and completely correct. I'm going to pause for a second because everybody's at different places. But now we're not done. We're like a step away from the final answer. But if anybody else wants to take over or do it themselves for themselves or for the group, like somewhere from this 6.9, and obviously I know that Ardell did it. Somewhere Ardell got from this 6. So what she's saying is, in the end of the day, we got 6.92 meters to the east, as well as at the same time getting 9 meters to the north. Somehow from that, she got that we did a total of 11.4 meters totally, and we did it at some sort of northeastern angle. I'm going to look in the chat. Oh God, there's a lot in chat. I'm sorry. I'm going to shut up for a second. Lordy, hold on. Oh, sorry. I'm saying the wrong. Wait, wait a minute. I think I think this joke is ahead of my, so I think someone is like being supportive and compliment. Wait. Oh, okay. But I'm not using anybody's name wrong, right? Am I using anybody's name wrong? Is that, I'll continue.
No, I made a typo.
Okay, no, fine. As long as, because okay, I'm just gonna keep going, but this is great. And I'm not gonna. Do you know that should I say that? When my wife and I met, and when we had our first, like years ago, obviously, like we have kids and everything, but like when we first met on our first date, our big excitement at the time was that neither of us had ever been on Facebook. This was at the time. And then that was even mentioned at our wedding that neither of us at the time had ever been on Facebook. Now, why I'm bringing this up right now is, first of all, it's still true to this day that I've never been on Twitter. So anything with @, I'm still like a little bit confused about like hashtags and all that. But the second thing is, for whatever it's worth, to this day, I still haven't ever been on Facebook. And I don't know if that's good or bad, but it's just true. And it's irrelevant, except that whenever I see any symbols, I don't know if someone's, it's always possible that it's a joke I don't get. Anyway, all right. Anyway, so what I think Ardell did next, or what certainly I'm doing next, is then we take the results. We take the results of that chart. Like the chart is a way of dividing the X world from the Y world. But then at the end of the day, the X world and the Y world did happen at the same time. That's what we're saying in physics. And it really is a major thing that comes up all the time, that we're saying all axes occur at the same time, but independently of each other. They don't affect each other. You don't communicate. So therefore, at the end of the day, to put them together, we're going to take the chart literally. We're going to say, the chart says that at the end of the day, we went 6.92 to the east. And notice, this is an example of where I always draw the horizontal first. Like everything I'm saying here can make sense to people if they've never done it before. But if you don't try it on your own, you might not realize that a lot of what I'm drawing and saying here, and a lot of what Ardell here's the other thing, why I got so crazy about what Ardell said. There's a ton of things she said in there that each one represents a choice that she made on a piece of paper or with a drawing or with a calculation. And each of those choices, you don't even know it's like a choice until you do it on your own and you realize how many choices there are to choose from. And like, in other words, here's this triangle that I'm drawing from her results. I'm saying draw 6.92 to the east. Then from the tip of that arrow, start the tail of an upward arrow that goes up 9, that goes up 9 to the north. And if you draw that, then what we're saying is your final answer. The final answer to this whole thing, how far the guy got, or I got, is the Pythagorean sum of those two legs. Like, yes, it'll be the hypotenuse of this triangle. And the ultimate, and so that's where she got the 11.4. Like we do the square root of 6.92 squared plus 9 squared. Like this squared plus that squared, square rooted will be the final distance. And you get this number like 11.4. It's, you know, it's not as big as 13 because we didn't walk 5 and then 8 all in a line. We walked 5 and then 8 on this cockamamie angle. So we walked a total of 11.4. Then to get what the total angle was that we did, in other words, if we had just wanted to go directly to our final destination and there had been no buildings to worry about, if we were allowed to just go straight, what would straight mean? Well, it apparently means the thing she said, 52.4 degrees northeast. Now, how do I get that? First of all, I know it's northeast because that angle literally is a northeastern angle. Like if I'm taking my arrows seriously, if I'm drawing arrows in the positive or direction that they're supposed to be drawn, and if I draw the horizontal first, then that angle between the tail, you'll know you've done something right if the angle between the tails of the two final vectors, the angle between the tails, yeah, you'll know you've done something right if the angle between the tails is the angle from horizontal. You'll know you've done something right if the angle, and by the way, all of these, this all looks like math. This looks like geometry, and trigonometry. It looks like right triangles, and it totally is. But where it's physics is, you cannot, this is where I'm so obnoxious on exams, and I feel bad, I'm saying this in advance. Where I take off points on exams where people often feel like it's very picky and unfair or something, is that I will not accept any triangles that are just raw triangles with sides. All the triangles have to be made up of arrows that have tips and tails, because that's like actually the purpose of this whole thing is to get directions right. So if we actually, every time we draw a line, actually draw it as an arrow that's pointing in a deliberate direction based on our positives and negatives and everything, then I have this eastern arrow. From the tip, I drew a northern arrow. The arrow from the original tail, the angle between the, so the final arrow that goes from the original tail to the final tip, like that arrow does represent the answer. And its direction should be the angle between the two tails. Like I'm not looking at this angle. People often ask, like, which angle? I get it, but I never know what angle to look at or whatever. Well, this is the right angle. We're never dealing with the right angle. We just need the right angle. But as to which of the two remaining angles to analyze, we've done things correctly if the angle between the tails ends up at the horizontal. We always want an angle measured from the horizontal, because this means if we now do inverse trig like she did, and like maybe I'll try to do one step slower in a moment, but if we literally say, okay, tangent of this angle equals, say, opposite over adjacent. So if we say right here, tangent of the angle equals opposite 9 over adjacent 6.92, then the angle itself is the inverse tangent. On the calculator, you have to do 9 over 6.92, and that will give you the tangent of the angle. So you have to take the inverse tangent of that, the arc tangent of that, and this will happen every time. The arc tangent of that, or the second tangent, or the tan to the -1, however you say it on your calculator, the arc tangent of 9 over 6.92 is the angle we're looking for in degrees. And we get, like what Ardell said, like around 52 or 53 degrees. And that's the final answer, but it's 52 degrees northeast, because there it is, some amount that's being opened north of east. what I just want to call, and I'll go back to this picture. So that's, sorry, I'm saying too much. So the answer to the whole problem is, the answer is 11.4, approximately 11.4 meters in what direction? In a direction of approximately 52 or whatever, yeah, 52.4 degrees northeast. Like all of this information taken together is the answer. It is a magnitude with an angle with points of the compass, all together necessary to fully specify what we would have done if we traveled as the crow flies, so to speak. Like if we had just gone straight from the original starting position to the final landing position, if we had gone from the first tail to the very last tip, if we had gone straight, what we would have done is gone 11.4 meters at an angle of 52.4 degrees northeast. I know I'm talking a lot. Last thing I want to say about that, and I can go back to that page, but look at this original. Yeah, I just want to alert everybody, this picture, which I did not stop and dwell on, is a picture, something like this is a picture that many of you may have drawn at the beginning and should have. This is a great picture of the situation. This is a very important, informative picture of the situation. That in fact, I will ask, even if we now, again, I'm saying the answer is approximately 11.4 meters at approximately 52.4 degrees northeast. So that's the answer. And that means that that is the size and the orientation of that dotted white arrow in that picture. Like, so what I'm about to say is, here's another picture, a good way of looking at things, but it also has limitations that I have to make clear. This picture here is a picture of the whole situation. Like I walked 5 meters north and then I walked 8 meters at 30 degrees northeast. So I put those two vectors tip to tail, and I drew them really big. And let's say I used graph paper, and let's say I even used a protractor to draw that second one. So let's say I tried really hard to draw them, really at scale, like really accurately. Excuse me. Excuse me. I can't get. I guess I can't pass germs through the internet. Well, all right. Anyway, I feel like I should put my mask on while I'm anyway. If I draw this picture, what is correct and what's super important about vectors is we really believe in vectors. Like vector quantities are things like displacement, velocities, like numbers with directions. But these arrows, these vector arrows that we draw, they are our calculators. They literally are. Like we really believe that if we draw them to scale, tip to tail, then we can, from our drawing, get answers that we would otherwise need digital modern electronic calculators to get. And remember, all this physics has we've been doing this physics for hundreds and hundreds of years, way before there were calculators. And we've been doing this math for thousands of years before there was calculators. So there's a way people got these answers, and the way they got them was literally from the drawings. That's how much we trust the operate. In other words, placing two arrows tip to tail is literally adding two vector quantities. We could get Ardell's 11.4 and our 52.4 if we just measured this final white dotted line super accurately. But, so that's, okay, that's the good news, is like this diagram right here does represent the whole situation. But now let's be really careful about this whole diagram. It was not her, like she discussed much more than just this triangle. She brought in other triangles that we just used. Like she broke up the 8 itself into a 6.92 and a 4. That is not obvious in this triangle. This is what I want to say to everybody. This thing that is drawn here is how to look at the whole situation and how to graphically represent the whole situation. Notice, but it can't be used to solve. We can't literally just jump to the answer by solving. Many people, what they might like to do, for example, is think, oh, 5 squared plus 8 squared square rooted will be the answer. Like they might want to do Pythagorean theorem to this 5 and this 8 in order to get that third leg of that third side of the triangle, the white line, but that doesn't work. Don't do that, because this big triangle that we have staring us in the face here is not a right triangle. Like one of the things that was really right about what Ardell did is we definitely need to use right triangle math to solve any vector problem. But where we will find our right triangles is each individual vector is its own hypotenuse. like there aren't automatically necessarily right triangles just staring us in the face where we put different vectors together. Another way of saying what I'm trying to say that's super important is notice in that second vector, notice when I drew the 8 meters at 30 degrees, notice it is at 30 degrees from the horizontal. It is not 30 degrees from the other vector. Super important. If you draw it 30 degrees from the other vector, all of a sudden it's a whole different, like that's not what the 30 degrees means. It's not a relationship to the other vector. It's just what direction the second vector is pointing in and of itself. So I draw it relative to this imaginary horizontal. Now, you could, with this picture is simple enough. If you're smart enough to know it's not a right triangle, what anybody might do is some other stuff, like they might do law of cosines. Technically, honestly, that actually does work. It's a mess, and I don't want anybody to have to know the law of cosines in this class. But in this particular situation, you could use the law of cosines and like force your way to the same answer that Ardell got. You could get an answer for the size of this last side. But first of all, it'll only work in this situation. It won't work in other situations. And I don't want you to have to know the law of cosines, especially if it doesn't work most of the time. But then also, I just want to make clear to everybody, this thing right here, like that is not an angle that means anything at all. Like what people would tend to do is solve for that angle and think it's the final angle answer. It's not. That is some kind of east-north angle that doesn't represent anything about what we want in the end is this angle here. We want to know how far north of east that white arrow sent us. Like we want an answer like 52.4 degrees northeast. If anybody got as a final answer something like 38 degrees, that would be this angle here, and that would be 38 degrees east of north, right? If that makes, and that's not the way people talk. Anyway, so to add vector quantities, we do place vector arrows tip to tail. This diagram depicts the addition of the whole situation, but to do the addition, to actually get the answer, we resolve each individual vector into components. That's what Ardell did. So we start with this big picture. I know you totally can't read. Hold on. Neither can I. Sorry. So we draw this big picture here on this page to represent the whole situation, but to actually get the numbers and do the math, we take each vector, zoom in on it, and resolve each individual vector into its individual components. And any vector that looked like she did, like she took the 8 and divided, and separated it into 2 legs. She made the 8 the hypotenuse of its own right triangle and found its 2 legs using direct SOHCAHTOA. And then she added up everything, put the answers, took all the answers and made one big right triangle, which she then solved using SOHCAHTOA in the other direction. Like that is what we'll do every time. We're going to break up vectors into individual triangles and then put them all back together to one big triangle, because we believe that the XY world is really the X world and the Y world happening independently but simultaneously. That's the summary of this. Wait, I think that's all I want to say for the moment on this. So I'm going to breathe for a second. So I hope I'll let this sink in with everybody. I'm like, look and see if you have any questions. Again, this method, if you get it, would work. We could add up 3 vectors, 4 vectors. We could add up velocity vector, any kind of vectors at all, any number of them. If you get this method, you'll see how it could be applied to anything, which of course is where we'll go next, is to a slightly more complicated problem. So before they do that, before I go to a next more complicated problem, and before I keep congratulating anybody on what they've done already, which is great. And super, really, this was, usually this takes a long time in a class to get to this point. That was like super fast. If anybody feels like they know whether you got it that fast on your own, if you feel like you know what I'm saying at all at this point, then you're definitely getting this in a nice pace. So the next problem will be slightly more complicated, but I'm going to hold for a second and just let you look at this, see if there's any questions or whatnot. But then if there aren't, we're going to do one more problem, slightly more complicated. And of course, that'll be as far as we get today. And then I'll post everything. So I'm going to walk away for a second and let you think. But then.
Hey, Ardell, is there any way you could show your work? Because I am so confused. I don't understand, like, how he did it. Sorry to put you on the spot.
That's okay. It's okay. I don't know if you could. Let me see if I can do it.
Wow. Wait, but sorry, whoever just said that, and right, and Ardell can do whatever she wants with that. She can like try or not, because right, but whoever just asked her, totally, that is point. I mean, and I appreciate that the person just also apologized to not want to put Ardell on the spot, but yeah, to want to see more of that. Who just asked that? Because I walked away. Who asked Ardell that?
Hey, it was me. It was Jamie.
Oh, great. All right. I want it to be clear. That is total. Please submit that for point. Like, please write down that you did that. Like, even if she says no, which would be fine. I really appreciate that you did ask for that. So please put that in for points, so to speak.
I cannot tell if it's showing or not. You gotta let me know if I should flip my camera.
Well, no, I don't think we could see it. I'm so touched that someone asked that. What I'm going to try to do. Oh, wait, one thing. Wait, I can, if she submits it, I could probably share what she did electronically, like next time, if it helps anybody, but I don't know if, but you would have to submit it to me to do that. But one thing I can try to do now is maybe draw, these diagrams got so complicated. I'll try to draw one more that will be a cleaner picture of maybe what she did, but I can't, you're right. I would love to see, I'm sure it will be more helpful to see her exact work than mine. But I think what she's saying is this. I mean, wait, Ardell, would you agree? Oh, wait, wait. Wait. So I'm looking at the chat. I'm a little, right. Wait. Okay. Right. And again, right. I want to be careful. I don't want to put anybody on the, it's true that if, and we could just work on this for all of us for next time or something. It's true that in principle, if anybody takes a picture of their work, they could, if they take a picture of their work into their computer or their phone, then as long as they have the picture in the same device as the Zoom, they could post the picture into the chat, or they could send it in Google Classroom to me, and then I can screen share it. But no one has to do anything like that. I don't think that through Google Classroom we can directly, I don't think in Google Classroom we can directly do this chat.
You could actually, if you go in the app and you go to the class, it says share something with your class, and then you could just add an attachment.
Right. You're saying she could do, I see what you're saying. Yes.
And it'll post to the whole class.
Okay, right. Totally. And if so, great, I see. And if she does, and then I've got it, then I can also look. So again, like if either right now or later, or if any of you ever wants to, I think I do want to encourage that, but I also don't want to like anybody to feel forced to. so we'll see what happens with there. For the moment, I think one of the key things that we might find in a drawing of hers, I think one of the key drawings is this thing on the board. I don't know if it captures, but one of the main things you got to do to add these two vectors together, and again, we're going to do more exercises like this in a way for the rest of our lives, but the key thing is to take the individual vectors, every single one of them, and break them up first. And any vector that seems hard to break up, like the 5, any vector there you're like, wait, I don't even know how to break this up, probably means you don't have to break it up. There's nothing to break up. Like the 5 is just literally pointing. And again, this is what Ardell said. The 5 is just pointing 5 meters to the north. It's not doing anything to the east or west. So the answers for east and west is 0. But this 8 is where the issues come in. Like, yeah, I would love to see her, she may have drawn it in a way that would more directly communicate with some of you, but the drawing has something to do with what I've done here. Like, you take the 8 that's pointing at 30 degrees northeast. And again, it's key to understand that that 30 goes with the 8. Like the 30 comes with the 8. It's saying that the 8 vector points that way, regardless of any other vector in the world or anything else that's going on. The 8 just points that way. So the 8 is like a hypotenuse at 30 degrees north of the east line, but the east line and the north line, like, they form a right angle. And this is always like every single vector that I ever look at, if it's tilted at all, if it's not just pointing along one axis, then I'm always going to make it into its own little individual right triangle. I'm always going to take any random vector and say it's pointing somewhat to the north and somewhat to the east. North and east make a right angle together. So any random vector I have a hypotenuse, assuming it told me its magnitude and its direction, its angle. I've got this size of the hypotenuse, 8. I've got the size of this angle, 30 degrees. So now I'm saying, or she's saying, that the 2 legs of this right triangle can be gotten from SOHCAHTOA. I mean, that's what's happening here. And we're literally saying sine of 30 is equal to we're saying sine of the angle is equal to opposite over hypotenuse, which in this case means the y leg over the 8 leg. So I'm multiplying both sides by 8, by the hypotenuse, and saying, oh, then 8 sine of the angle, whatever it is, will equal the y leg, the y component. Like, and similarly with adjacent and cosine. And I'm always going to do that. Like, SOHCAHTOA is now important in my life as a physicist. I will, for any given vector I'm given, I will know the angle. I will know the size of the hypotenuse. I will thereby figure out the legs. Like, I'm always doing SOHCAHTOA this way, using it to get the legs. And the legs of this triangle are then 4, like if I do it on a calculator in degree mode, sine of 30 is 1/2 times 8 is 4. And cosine of 30 is like 0.866 times 8 is like 6.92. So the 2 legs of that triangle are 6.92 and 8. I mean, that's, again, right. I could totally I don't even remember, right. You could totally post it on the stream. If I get a digital copy of this, I could totally post it on the stream. I can also share it right here. I don't know if you guys, I don't even remember if you guys can post attachments into the stream. Knock yourself out. Please do if you can. But what I think I'm going to do now, and again, I don't want to, and I feel a little bit, this is great. And I hope everybody understands that everybody who's like pointed out things today, even if they're pointing out things about how to chat in Google Classroom or whatever, all of that is points. Like, it's not, I mean, there's definitely like, there was I mean, if this is a Broadway musical, there might have been a star of the show today, but there isn't only just one star, blah, 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 metaphor, something, something. So what I'm trying to say with that is, with the 10 minutes left, I'm going to take the risk of, I am going to move on and give one more exercise to everybody so you can all see if you get this or not. The only thing, I'm not going to make it crazy hard or crazy tricky. I'm going to write one more exercise. The one thing I'm going to add is that, the one thing that will increase the stakes, not the difficulty, is that this one exercise we're going to put now will have 3 vectors in it rather than 2. Okay, that's the only difference. I'm going to write the exercise out. I'm going to solve it while you're doing it. And even if we don't have time for a big discussion or whatever, before it turns 1:30, I will just write what I think the answers are, so we can just all see where we are with this. Even if it doesn't get a total explanation, or if even people don't get total points, you'll at least see where we are with this. And then, and so again, and again, if by next time, if we either all have worked out how to share screens with each other better or something, great. Or if Ardell ends up posting something in stream because she feels like it, then great. And I'll totally use it next time. But if not, blah, blah, blah. Maybe it already happened even as I'm talking. But here's the last exercise that we'll do today that, again, I'm just going to write, and then I'm pretty much just going to solve, like, then I'll, we probably won't talk about it much, but you'll know if you got it right or wrong. It's this. And what we're doing right now is technically we're adding displacement vectors. We're learning how to add displacement vectors by the component method. But this method, if you feel you understand it by the end of today, works for any kind of vectors at all. So here's the example. Sorry. Okay, this is the problem. Again, we have very limited time. I'll pick up from this next time. Like I'll start with this next time going over it. But it's the same question as before. Find the total displacement, which just like before means a total magnitude and a total angle, like with points of the compass. So you're gonna have to get a size. And again, this is what we'll pick up next time. So please, if you don't finish this now, like consider this homework, whatever. Maybe I'll even put in a portal to like just submit this, or if you remind me, I will, even if you submit it next time. But we have 5 minutes. I'm going to try to give an answer right. I will give an answer in the next 3 minutes. So again, you can check see if you're on the right track or not. But it will take work to get this. You're going to add 3 vectors together to get a final vector with size and direction. So again, you know what you have to do now in principle, just turn back to your notes from before, but you're adding 3 things rather than 2, but it's the exact same method. Again, I'm going to shut up and try to solve this. I mean, I will solve it on a separate piece of paper, but all I'm going to write is the answers. I will make a portal. I will remind me, but I'll open up a portal so you can hand this in for credit, as well as in addition to adding in for submitting for participation stuff. But yeah, we're going to end with the answer to this. I'm just going to solve. I'm going to shut up. We have like 4 minutes to do this. And please just remember there's a south mentioned and there's a west mentioned. So remember negative signs, like somewhere they matter. But Huh. Huh. I'm loving this chat. I love this class. This class is, first of all, you're getting A's, but second of all, you're all going on the express train to heaven. And that includes Ms. Ortega. This class is awesome. And I'm going to write the answer. Now, maybe I made a mistake on it. I'm about to just write the answer. And again, I'm going to open a portal for this. I'm going to write the answer. That should spoil nothing for no one. Like, I'm just writing the answer. It takes a lot of work to get there. So you could submit all the work and totally get full credit for, like, I'll know you got it right from all the work. Or if you're wrong, you can correct based on this answer. Also, maybe I made a mistake, although I don't think so. But anyway, so I'm just going to write the answer so you have a reality check, but you could submit this for next time. We'll pick up talking about it for next time. I really want to thank you, but here's what I think the answer is. The total displacement from the 3 vectors. And I'm not showing how I'm just saying the answer, I believe, is approximately 6.6 meters, a little bit more than 6.5, 6.6 meters at approximately 9.26, which is very small northeastern angle, like it's almost due east. That's what I think the answers are. I'll check. Ooh, wait. Oh, yeah, it is possible. So check. So I'm not even gonna look. Yeah, it is possibly switching, but I definitely appreciate that. That's fat. Right, maybe, very possible. Definitely check, and I'll check too. But I think that's the answer. And I'll check, and when I make a portal, I'll check if I did it wrong. I think I did it right. But I'm also going to go now to keep my promise to everybody. I think this is great. Again, if we need appointments or recommendation or things like that, or if you send me an email and I didn't respond, it's great that I apologize, but you put in the private chat and we'll work out whatever it is, or just remind me to blah, blah. But great job, everybody. Seriously. I'm going to leave before I'm pushing my luck, but I'll post the recordings and I'll post this and blah, blah, blah. Goodbye.